our chapter X blocks from physical chemistry. The elements belonging to group 1 or 2 of the periodic tables are called S block elements. These have 1 or 2 electrons in their outermost s orbitals. Group 1 elements are called alkali metals and have the general electronic configuration NS1. These constitute 6 elements, namely lithium, sodium, potassium, rubidium, cesium, and francium. These are called alkali metals because they readily form oxides and hydroxides which are alkaline. The group 2 elements of the periodic tables are called alkaline earth metals and they consist of the elements beryllium, magnesium, calcium, strontium, barium, and radium. Their general configuration is noble gas NS2. These elements of group 2 are also metals. The oxides of some of these metals were known much earlier than the metals themselves, and these were called alkaline earth metals because these were alkaline in nature and existed on the earth. In this present unit, we will have a comparative study of the elements of these two groups and some of their silent features. Abundance and occurrence. The alkali and alkaline earth metals are the most violently active of the metals. These are readily oxidized and therefore are not found in the free state in nature. These are found in the combined form with halide, sulfate, carbonate, silicate ions, etc. The abundance of alkali and alkaline earth metals in the earth's crust shows a good range. Among these, calcium is the fifth most abundant element in the Earth's crust and hence the third most abundant metal after aluminium and iron. Vast sedimentary deposits of CaCO3 occurs over large parts of the Earth's surface. Magnesium is the sixth and sodium is the seventh most abundant element in the crustal rocks. These are fourth and fifth most abundant metals after aluminium, Fe, and Ca. Potassium, eighth, is the next most abundant element after sodium. There is unlimited supplies of NaCl in nature, in natural brines and oceanic waters. The occurrence of other metals in the Earth's crust is very poor. Francium and radium are radioactive and have rare terrestrial abundance. Beryllium is rare and radium is the rarest of all, comprising only 10 raised to power minus 10% of igneous rocks. The abundance of group 1 and group 2 elements in crustal rocks are given below in ppm. This is the group 1. Lithium have 18, sodium is have 22,700, potassium have 18,400, rubidium has 78, cesium has 2.6, francium has 2 into 10 raised by minus 18. In group 2, BE have 2, MG have 27.640, 2700 640, CA have 46,600, SR have 384, BA have 390, RA have 1 into 10 raised to power minus 10. Electronic configuration. All the alkali metals have one electron in their outermost s orbitals, while the alkaline earth metal have two electrons in the outermost s orbitals preceded by noble gas configuration. Their electronic configuration are given in table 1. First is group 1 alkali metals. Elements are lithium, atomic number 3, electronic configuration helium 2s1, sodium 11, Ne3s1, potassium K 19, Ar4s1, rubidium 37, Kr5s1, cesium Cs 55, Xc6s1, francium Fr 87, Rn S71. S71. Element beryllium Be, atomic number 4, electronic configuration He2S2. These are alkaline earth metals. Magnesium Mg12 Ne3S2. Calcium Ca, atomic number 20, electronic configuration Ar4S2. Element strontium Sr, atomic number 38, electronic configuration Kr5s2. Barium Ba, atomic number 56, electronic configuration Xc6s2. Element radium Ra, atomic number 88, electronic configuration Rn7s2. Comparative study of general characteristics of group 1 elements. The important physical constants of alkali metals are given in table 2 and the general characteristics are given below. This is the table. No. Physical properties. First is atomic and ionic radii. Alkali metals have the largest atomic and ionic radii in their respective period. On moving down the group, the atomic and ionic radii increases. This is due to the fact that the alkali metals are the first elements of each period. As we move in a period, the atomic radius and radius tends to decrease due to increase in the effective nuclear charge. Therefore, the alkali metals have the largest atomic and ionic radii in their respective periods. On moving down the group, there is an increase in the number of shells and therefore atomic and ionic radii increases. Second is ionization energy. Alkali metals have the lowest ionization energy in each period within the group. The ionization energies of alkali metal decreases down the group. Atoms of alkali metals are largest in their respective periods and therefore the valence electrons are loosely held by the nucleus. By losing the valence electrons, they acquire stable noble gas configurations. This accounts for their ease to lose electrons and hence they have low ionization energy. On moving down the group, the atomic size increases and the magnitude of screening effect, number of inner shells, also increases and consequently the ionization energy decreases down the group. The second ionization energies of alkali metals are very high. When an electron is removed from the alkali metals, they form monovalent cations which have very stable electronic configuration, same as that of noble gases. Therefore, it becomes very difficult to remove the second electron from the stable noble gas configuration, and hence their second ionization energy values IE2 are very high. For example, Na solid converts into Na positive gaseous plus electrons whose first ionization energy is 496 kilojoule per mole. And second, Na positive gaseous converts into Na2 positive gaseous plus electron. Their second ionization energy is 4563 kilojoule per mole. Third is melting and boiling point. All these metals are soft and have low melting and boiling points. The alkali metals have only one valence electron per metal atom, and therefore the energy binding the atoms in the crystal lattice of the metal is low. Thus, the metallic bonds in these metals are not very strong, and consequently their melting and boiling points decreases on moving down from lithium to cesium. Density. Fourth is density. The densities of alkali metals are quite low and as compared to other metals, lithium, sodium and potassium are even lighter than water. The densities increases on moving down the group. However, potassium is lighter than sodium. The densities of metallic elements depends upon the type of packing of atoms in metallic state and also on their size. The alkali metals have close packing of metal atoms in their lattice, and because of the large size of their atoms they have low densities. As we move down the group from lithium to cesium, there is increase in the atomic size as well as atomic mass, but the increase in atomic mass is more than the compensates the increase in atomic size. As a result, the densities, mass by volume of alkali metals gradually increases from lithium to cesium. However, potassium is lighter than sodium, probably due to larger increase in atomic size as compared to increase in atomic mass. It may be noted that it is quite unusual for metals to have low densities. For example, most of the transition metals have very high densities, more than 5 grams centimeter minus 3. For example, iron has a density of 7.9 gram, while mercury has a density of 13.6 gram. Fifth is electropositive or metallic character. All the alkali metals are strongly electropositive or metallic in character. The electropositive character of an element is expressed in terms of the tendency of its atom to lose electrons. As alkali metals have low ionization energy, their atoms readily lose their valence electrons. These elements are therefore said to have strong electropositive or metallic character. Since the ionization energy is decreased down the family, the electron releasing tendency or electropositive character is expected to increase down the family. Sixth is oxidation state. All the alkali metals exhibit an oxidation state of +1 in their components. The alkali metals have only one electron in their valence shell and therefore they can lose the single valence electron readily to acquire the stable configuration of a noble gas. Thus, they form monovalent ions. M positive example: lithium positive, sodium positive, potassium positive, rubidium positive, cesium positive. Since the second ionization energies are very high, they cannot form divalent ions. Thus, alkali metals are univalent and form ionic compounds. Seventh characteristics: flame coloration. All the alkali metals and their salts impart characteristic flame coloration. The alkali metals have very low ionization energies. The energy from the flame of Bunsen burner is sufficient to excite the electrons of alkali metals to higher energy levels. The excited state is quite unstable, and therefore when excited electrons come back to their original energy levels, they emit extra energy which fall in the visible region of the electromagnetic spectrum and thus appear colored. The different colors of the alkali metals can be explained on the basis of amount of energy absorbed for excitation of the valence electrons. Eighth is photoelectric effect. The alkali metals readily emit electrons when radiation strike on their surfaces. This phenomena of ejection of electrons when electromagnetic radiation strikes on the surface of metal is called photoelectric effect. Because of low ionization energies, the electrons of alkali metals can be easily ejected from their surfaces. Among alkali metals, cesium has the lowest ionization energy and hence it can show photoelectric effect to the maximum extent. Therefore, alkali metals, especially cesium, are used in photoelectric cells which are sensitive to blue light. Ninth is nature of the compounds. The compounds of the alkali metals are ionic in nature due to the low ionization energies and large atomic size. The atoms of alkali metals form cations readily by losing the valence electrons. Consequently, they form ionic bonds with the non-metals of the p block. Tenth is lattice energies. The alkali metal salts consist of cations and anions which are held up by a strong electrostatic force of attraction. Therefore, the lattice energies of alkali metal salts are very high. The lattice energy is defined as the amount of energy required to break one mole of a crystal into its free electrons, free ions. Therefore, the lattice energy gives a measure of the force of attraction between the ions. Larger the force of attraction, the greater will be lattice energy. The lattice energy also depends upon the size of the ion and its charge. For example, the cation of the same charge, the lattice energy of ionic solids having the same anion decreases with increase in size of the cation due to decrease in force of attraction between them as shown below. This Next is chemical properties. The alkali metals exhibit high chemical reactivity. This is due to first their low ionization energies, second a low heat of atomization. As the value of ionization energy decreases down the group from lithium to cesium, therefore the reactivity of alkali metals increases from lithium to cesium. The alkali metals are highly reactive towards the more electronegative elements such as oxygen and halogens. Some of their characteristic chemical properties are given below. First, Action with air. All the alkali metals get tarnished on exposure to air due to the formation of oxides at the surface. They burn vigorously in air or oxygen, forming three types of oxides. First, normal oxides containing O2 negative ion oxide ion. Second, peroxide containing O2 2 negative ions peroxide ion. Third is superoxides containing O2 negative ion superoxide ion. When the metals are burned in a free supply of air, the main product depends upon the metal. Lithium forms only the oxide Li2O and some Li2O2. Sodium forms peroxide Na2O2, while the potassium, rubidium and cesium form superoxides Ko2, RbO2 and CsO2 respectively. Now question arises why the lithium forms only normal oxide, sodium forms peroxide while others form superoxides. The formation and the stability of these oxides can be explained on the basis of size of the cation, alkali metal ion, and the anion. It is known that smaller cation can stabilize smaller anion and larger cation can stabilize larger anion. This is the basic of lattice energy effects. The normal oxides contains O2 negative ion. The peroxides contain O2 2 negative ion and superoxides contain O2 negative ions. Lithium ion is very small ion and therefore has strong positive field around it. Therefore, it can stabilize only a small anion O2 negative. In other words, because of small size of lithium ion, the spreading of negative charge towards another oxygen atom is prevented and therefore it cannot attach with another oxygen atom. Consequently, higher oxides are not formed. Sodium ion is large and it can stabilize large anion. The positive field around sodium ion is weaker and does not prevent the conversion of oxide ion into a peroxide ion, but it is strong enough to prevent further oxidation to superoxide ion. On the other hand, because of large size of K positive, Rb positive and Cs positive ions, the positive field is very weak and allows the superoxide ion to be formed. These are briefly discussed below. First, oxides. Pure Li2O is prepared by thermal decomposition of Li2O2 at 450 degrees Celsius. LiO, Li2O2 under 450 degrees Celsius gives the LiO plus half O2. Sodium oxide Na2O is prepared by the reaction of NaOH, Na2O2 or NaNO2 with sodium metal. NaO, Na2O2 plus 2Na gives the 2Na2O. NaOH plus Na gives Na2O plus half H2. NaNO2 plus 3Na gives 2Na Na2O plus half N2. The normal oxides of other alkali metals can also be prepared by similar reactions. LiO and Na2O are white, K2O is yellowish white, Rb2O is bright yellow, and Cs2O is orange. These are fairly stable towards heat and decompose only above 500 degrees Celsius. Second, peroxides. The peroxides contain peroxide ion O2 2 negative, which is isoelectronic with F2. LiO2 is prepared industrially by the reaction of LiOH.H2O and H2O2 and dehydration of the subsequent hyperoxide by slightly heating under reduced pressure. LiOH.H2O plus H2O2 gives the LiOOH dot H2O plus H2O. 2 LiOOH dot H2O gives by heating Li2O2 plus H2O2 plus H2O. It is thermodynamically stable while crystalline solid which decomposes to LiO on heating above 195 degrees Celsius. Na2O2 is prepared by oxidizing Na to Na2O in a limited supply of dry oxygen air and then reacting this further to give pale yellow powder of Na2O2. 2Na plus half O2 heated and give Na2O and then added half O2 and it gives Na2O2, which is pale yellow. The other alkali metal peroxides cannot be prepared by the above method because of their further oxidation to the superoxides MO2. These are best prepared by the quantitative oxidation of metals in the liquid NH3. Next is superoxides. These contain the paramagnetic O2 negative ion, which is stable by only in the presence of large cations such as K, potassium, rubidium, cesium. NaO2 is prepared by reaction of O2 with sodium dissolved in liquid NH3. It can also be prepared by reacting Na with O2 at 450 degrees Celsius and 150 atmospheric pressure. Other heavier alkali metal superoxides can be obtained by burning these elements in air. M2O3 have also been obtained as dark colored paramagnetic powders by careful thermal decomposition of MO2. These can also be prepared by oxidation of liquid ammonia solution of the metals or by controlled oxidation of the peroxides. These are considered to be peroxides, superoxides. The various types of oxides are distinguished by their hydrolysis reaction. M2O plus H2O gives 2M positive plus 2OH negative. M2O2 plus 2H2O gives 2M positive plus 2OH negative and plus H2O2. 2MO2 plus 2H2O gives 2M positive ions, 2OH negative ions, and H2O2 plus O2. The different types of oxides can be identified by these reactions. Second, action with hydrogen. The alkali metals react with hydrogen to form hydrides which are ionic in nature. First is the reactivity of alkali metals with hydrogen increases from lithium to cesium. Second, the ionic character of the hydrides increases from lithium to cesium. This is because of decrease in ionization energy down the group so that the electrons become easily available to hydrogen for forming H negative ion. Third, the stability of hydrides decreases from lithium to cesium. This is due to the fact that as the size of the alkali metals increases from lithium to cesium as the so that the mm, MH bond becomes weak. Therefore, the stability of hydrides decreases. Fourth, the hydrides react with water, liberating hydrogen. Lithium hydride is used as a source of hydrogen for military purpose and for filling meteorological balloons. Fifth, hydrides behave as strong reducing agents and their reducing nature increases down the group. Action with water. Alkali metals readily react with water to form hydroxides and hydrogen gases evolved. As the electropositive character increases down the group, the reactivity with water increases on descending the group from lithium to cesium. Lithium reacts somewhat slowly, but sodium and the other members of the family react so rapidly with water that the hydrogen gas evolved immediately catches fire. Thus, alkali metals cannot be kept either in air or in water. They are normally kept in kerosene oil. The hydroxides of alkali metals are strongly basic and the basic strength increases down the group. The MOH bond in the hydroxides of alkali metals is very weak and it can easily ionize to form M positive and OH negative ions. This accounts of their basic character since the ionization energy decreases down the group. The bond between metals and oxygen becomes weak, therefore, the basic strength of the hydroxides increases accordingly. Thus, NaOH is a stronger base than LiOH and so on. Fourth is action of halogens. The alkali metals readily combine with halogen to form ionic halides M positive X negative. The reactivity of halogen towards alkali metals increases on moving down the group. This is due to decrease in ionization energy or increase in electropositive character as we move down the group. All the metal halides are ionic crystals. However, Li lithium is slightly covalent because of the polarization. Li positive being the smallest cation has maximum polarizing power, and iodide ion being largest anion can be polarized to maximum extent. All the alkali metals halides except lithium fluoride are soluble in water. However, LiF is insoluble in water due to its high lattice energy because of small cation and anion. The alkali metal halides react with halogens and interhalogen compounds forming ionic polyhalides. Solutions in liquid ammonia. Alkali metals dissolve in liquid ammonia to give blue solutions which are conducting in nature. In solution, the alkali metal atom readily loses the valence electron. Both the cation and the electron combine with ammonia to form ammoniated cation and ammoniated electron. The value of X and Y depends upon the extent of solvation of the alkali metal ion and the electron respectively. The ammoniated electron is responsible for the blue color of the solution. The electrical conductivity is due to the ammoniated cation as well as ammoniated electrons. The dilute solution are paramagnetic because of the presence of free electrons. With increase in concentration, the paramagnetic character decreases. This suggests that in concentrated solutions, the ammoniated electrons form electron pair as 2 electron negative 2 electron NH3 whole Y gives the ammoniated electron pairs ENH3Y whole twice. Due to the presence of free or ammoniated electrons, these solutions behave as strong and valuable, powerful, and selective reducing agents. These solutions can reduce aryl oxygen to superoxide and peroxide ions without bond cleavage. These solutions can reduce metal ions to their unusually low oxidation states. On standing, the solution slowly liberated hydrogen as 2M plus 2NH3 gives the metal amine 2MNH2 plus H2. Next is reducing nature. Alkali metals are strong reducing agents. This is due to their higher ease to lose electrons. It is clear from table 3 that the alkali metals have high value of oxidation potentials and therefore these can be easily oxidized. Hence they have very strong tendency to act as reducing agent. Lithium is the strongest reducing agent. All these alkali metals are better reducing agents than hydrogen. E naught is equals to 0. Therefore, the metal react with compounds containing acidic hydrogen atoms such as alcohols and acetylene liberating hydrogen. Lithium is the anomalous behavior of lithium and diagonal relationships. 2. Lithium belongs to the alkali metal group 1 and has most of the characteristic properties of the metal of group 1. However, it differs from the remaining member of the group in many respects. This is mainly due to the following reasons. First, the size of lithium atom and its ion is very small. Second, it has high ionization energy and least electropositive character. Third, the polarizing power of lithium ion is quite high due to its small size, which results in the covalent character of its compound. Fourth, it has no vacant d orbital in its valence shell. Some of the important characteristics of distinction between lithium and the rest of the family members are given below. Lithium is the hardest of all the alkali metals. The melting and boiling point of lithium are much higher than those of the other metals of group 1. Lithium is the less reactive as compared to other metals and it does not get tarnished readily in air. Lithium forms only monoxides Li2O with oxygen while sodium forms peroxides Na2O2 and other elements form superoxides MO2. The salts of lithium have lower ionic character than salts of other alkali metals. This is because of high polarizing power of Li positive ion. It readily reacts with nitrogen forming nitride while other metals do not react. Only lithium combines with carbon and silicon, forming the carbide and the silicate. Lithium hydroxide and carbonate are unstable and decompose on heating, while the corresponding compounds of the rest of the family members are stable and do not decompose. For example, Li2LiOH gives the Li2O plus H2O. Li2CO3 gives Li2O plus CO2. Upon heating, lithium nitrate gives nitrogen oxide, dioxide and oxygen. Sodium nitrate and potassium nitrate, upon strong heating, form corresponding nitrates and evolve oxygen. The hydride of lithium LiH is more stable as compared to the hydrides of other members of the family. Lithium chloride and nitrate are soluble in alcohol, while the salts of sodium are insoluble in alcohol. Lithium hydroxide is much less basic than the hydroxide of other metals. Lithium fluoride, carbonate, hydroxide, oxalate are sparingly soluble in water. The corresponding salts of sodium and potassium are readily soluble. The Li positive ion and its compounds are more heavily hydrated than those of sodium. However, lithium shows diagonal relationships and magnesium with magnesium. Diagonal relationships. It has been observed that some elements of second period show similarities with the elements of third period present diagonally to each other through belonging to different groups. This is known as diagonal relationships. Thus, the similarity in properties of elements present diagonally is called diagonal relationships. This is shown below. Second period Li is- sh- shows the similarities from the third period of Mg. For example, lithium resembles magnesium, beryllium resembles aluminium, and boron resembles silicon. Causes of diagonal relationships. The cause of diagonal relationship is the similarity in properties such as electronegativity, ionization energy, size of atom or ion, electropositive character, polarizing power, etc. as discussed below. First, similar electropositive character. As we move from left to right in a period, electropositive character decreases, and while going down a group, electropositive character increases. Therefore, on moving diagonally, the two opposite tendencies decrease and increase almost cancel out, and the electropositive character is almost same as we move diagonally. Next is polarizing power. On moving from left to right in a period, the ionic charge increase while the ionic size decreases, thus causing an increase in polarizing power. On the other hand, uh, on moving down a group, the ionic charge remains the same while the ionic size increases, and therefore the polarizing power decreases. As a result of these two opposite charges along a period and down a period, on moving diagonally, these two effects partially cancel each other, and therefore the two elements have almost similar polarizing power. Thus the two elements show almost similar properties. It is quite interesting to note that the type of bond formed by the two elements and their properties are almost similar, even though they have different valencies. Diagonal relationships between lithium and magnesium. Lithium, which is quite anomalous in characteristics as far as alkali metals are concerned, exhibits diagonally similarity with magnesium, the second member of group 2 present in the third period. The common characteristics of the two elements are listed below. The atomic radii of lithium is 1.23 A, while that of magnesium is 1.60. The ionic radii of lithium is 0.76, is quite close to that of magnesium 2 positive and 0.72. Both these metals are quite hard in nature. The electropositivities of Li 1.0 and magnesium 1.2 are not much different. Both Li positive and Mg2 positive Ions have polarizing power and almost same magnitude. Both LiOH and MgOH2 are weak bases. Lithium forms monoxide LiO. Magnesium also prefers to form only the monoxide MgO. The carbonates of both elements evolve carbon dioxide on heating. The hydroxides of both these elements decompose on strong heating. The hydroxides of other alkali metals are stable to heat. The nitrates evolve nitrogen peroxide and oxygen upon heating. 4LiNO3 gives 2Li2O plus 4NO2 plus O2. 2MgNO3 whole twice gives 2MgO plus 4NO2 plus O2. Both Li and Mg react with nitrogen to form corresponding nitrates. 6Li plus N2 gives 2Li3N. 3Mg plus N2 gives Mg3N2. Lithium chloride, like magnesium chloride, is diliquescent. Liquid hydroxide, like magnesium hydroxide, is a weak base. Lithium hydroxide, fluoride, phosphate, oxalate, carbonate are much less soluble than the corresponding sodium and potassium salts. However, the solubilities are comparable to those of corresponding magnesium salts. Comparative study of general characteristics of group 2 elements. The important physical constants of alkali metals are given in table 4 and their general physical characteristics are given below. Physical properties. First, atomic and ionic radii. The atomic and ionic radii of the members of the family are smaller than the corresponding members of the alkali metals. The alkaline earth metals have a higher nuclear charge and therefore the electrons are attracted more towards the nucleus. As a result, their atomic and ionic radii are smaller than those of the alkali metals. On moving down the group, the radii increases due to gradual increase in the number of shells and the screening effect. Second, density. Alkaline earth metals have low densities but the relatively more dense than alkali metals. This is because their atomic sizes are smaller than the corresponding alkali metals. Density decreases on moving down the group up to calcium, but it then increases considerably up to radium. Third, melting and boiling point. Alkaline earth metal have low melting and boiling point which are higher than the corresponding alkali metals in the same period due to comparatively smaller size. However, melting and boiling points do not show regular trends. The atoms in alkaline earth metals have smaller size as compared to alkali metals. Therefore, they are more closely packed in their crystal lattice and hence they have higher melting and boiling points. Ionization energy. The alkaline earth metals have low ionization energies due to fairly large size of the atoms. Since the atomic size increases down the group, the ionization energy decreases. A comparison of the ionization energies of the members of group 1 and 2 shows that the members present in the second group have higher values as compared to those of group 1 because they have smaller size and electrons are more attracted towards the nucleus of the atoms. It may be noted that although IE1 values of the alkaline earth metals are higher than those of the alkali metals, the IE2 values of alkaline earth metals are much smaller than those of alkali metals. The ionization energy of values of sodium and magnesium are given ahead. IE1 of sodium is 496 kilojoule per mole. IE2 of sodium is 456 4564 kilojoule per mole. IE1 of magnesium is 738 kilojoule per mole. IE2 of magnesium is 1451 kilojoule per mole. In case of alkali metals, the second electron is to be removed from a cation which has already acquired a noble gas configuration. On the other hand, in the alkaline earth metals, the second electron is to be removed from a monovalent cation which still has one electron in the outermost shell. Thus, the second electron in Mg and can be removed easily. The IE3 of magnesium will be very high because the electron is to be removed from stable noble gas configuration. Fifth is electropositive and metallic character. Because of the low ionization energies of alkaline earth metal, they are strongly electropositive in nature. However, these are not as strongly electropositive as the alkali metals of the group 1 because of comparatively higher ionization energies. The electropositive character increases down the group, that is from Be to Ba, beryllium to barium. Sixth characteristic flame coloration. Except for beryllium and magnesium, the alkaline earth metal salts impart coloristic colors to the flame. Seventh, tendency to form bivalent ions. The alkaline earth metal exhibits a valency of plus 2 as they can lose 2 electrons and form bivalent ions. Inspection of table 3 reveals that the second ionization energy IE2 of alkaline earth metal is greater than the first ionization energy IE1. It thus appears it thus appears that if ionization energy is the only factor involved in the formation of divalent ions, we would accept that alkaline earth metals would prefer to form plus 1 ion rather than plus 2 ions. Actually, they predominantly show plus 2 valency. This can be explained as divalent ions have the stable noble gas configuration. In solution, the plus 2 ions of alkaline earth metals are extensively hydrated, and the high hydration energies of M2 positive ions make them more stable than M positive ions. It is observed that the amount of energy released when M2 positive ion is dissolved in water is much more than that for M positive ion. This large amount of extra energy released in the hydration of plus 2 ion is more than compensate the second ionization energy required for the formation of such ions. In the solid state, the divalent cations form stronger lattice than monovalent cations, and therefore a lot of energy called lattice energy is released. It is greater lattice energy of M2 positive ion which compensates for a high second ionization energy and is responsible for its greater stability as compared to M positive ion. Next, chemical properties. Because of their low ionization energies and high electropositive character, the alkaline earth metal have strong tendency to lose valence electrons. Therefore, they are very reactive. The reactivity of these elements increase on going down the group. However, alkaline earth metals are in general less reactive than alkali metals. The chemistry is mainly dominated by the dipositive oxidation state. Some of the general trends are discussed below. First, action with air or oxygen, formation of oxides. The alkaline earth metal, being less electropositive than alkali metals, react with air or oxygen slowly upon heating to form oxides, ammo. However, Ba and Ra form peroxides. The reactivity with oxygen increases as we move down the group due to increasing electropositive character of the elements. The monoxides can also be prepared by decomposition of their carbonates. Among the oxides, BeO is amphoteric, while oxides of other elements are basic in nature. The amphoteric character of BeO is supported by the fact that it reacts with acids as well as alkalis. The increase in basic character of oxides from Be to Ba is because of decrease in polarizing power with increase in ionic size. The oxides of Be and Mg are almost insoluble in water, while the oxides of rest of the metals dissolve in water to form hydroxides. The insolubility of Be and Mo in water is due to their large lattice energies. Second, combination with hydrogen form of hydrides. All the elements except beryllium combine with hydrogen upon heating to form ionic hydrides. BeH2, however, can be prepared by the reaction of BeCl2 with LiAlH4. 2BeCl2 plus LiAlH4 gives 2BeH2 plus LiCl plus AlCl3. BeH2 and MgH2 are covalent while all other hydrides are ionic. Calcium hydride is known as hydrolith, and the hydrides are highly reactive with water and form hydroxides and liberate hydrogen. CH2 plus 2H2O gives CaOH twice plus H plus 2H2. Third is action with water, formation of hydroxides. The alkaline earth metal have lesser tendency to react with water as compared to alkali metals. They combine with water slowly to form hydroxides. Ca plus 2H2O on heating gives CaOH twice plus H2. Magnesium does not react with cold water but it decomposes hot water. Mg plus 2H2O hot gives MgOH twice plus H2. Mg plus H2O gives MgO plus H2. Like alkali metals, the hydroxides are basic in nature and basic strength increases down the family. The basic character of hydroxides is due to the low ionization energies of these metals. Because of low ionization energies, the MO bond in MOH is weak and it can cleave to give OH negative ion in solution. Since the ionization energy decreases down the family, therefore, the basic strength of the hydroxides increases. For example, BeOH twice is amphoteric, MgOH twice is midly basic, while other are strong bases. The hydroxides of alkaline earth metals are less basic than alkali metals of the corresponding periods. The basic strength of hydroxides of alkaline earth metal hydroxides is due to their high ionization energy, small ionic size, and positive charge on the ion. As a result, the MO bond in these hydroxides is relatively stronger than that of corresponding alkali metals and therefore does not break. Therefore, they are less basic than corresponding alkali metals. The hydroxides of alkaline earth metals are less soluble than alkali metals hydroxides. However, the solubility of hydroxides in water increases with increase in size of the metal. BeOH twice and MgOH twice are almost insoluble. CaOH twice is sparingly soluble while SrOH twice and BaOH twice are fairly soluble. This trend is due to increase in size of the cation and moving down the group so that their lattice energies decrease. Due to decrease in lattice energies, the hydration energies become more and more, and the solubility of hydroxide is in water increases. Fourth, action with nitrogen. The alkaline earth metal react with nitrogen to form nitrides M3 and 2, which reacts with water to liberate nitrogen. 3Ca plus N2 gives Ca3N2. Ca3N2 plus 6H2O gives 3Ca OH twice plus 2NH3. Be3N2 is volatile whereas other nitrides are non-volatile. Fifth, formation of halides. All the alkaline earth metals combine with halogens at higher temperature forming their halides. M plus X2 gives MX2. X can be chlorine Br. The metal halides can also be obtained by the action of halogen acids on metals, their oxides, carbonates, and hydroxides. MO plus 2HX gives MX2 plus H2O. MOH twice plus 2HX gives MX2 plus 2H2O. Anhydrous beryllium halides cannot be obtained from materials prepared in aqueous solution because of the formation of hydrated ion. The hydration of these products result in hydrolysis. BeH2O whole for Cl2 on heating gives BeOH twice plus HCl. On hydrous beryllium, the anhydrous beryllium fluoride and chlorine can be prepared by the following methods. BeO plus 2NH4F gives NH4 twice BeF4. On heating, it gives BeF2 plus 2NH4F. BeO plus C plus Cl on heating between 600 Celsius to 800 degrees Celsius gives BeCl2 plus CO. 2BeO plus CCl4 on heating 800 degrees Celsius gives 2BeCl2 plus CO2. Among alkaline earth metals halides, except beryllium, the chlorides, bromides, and iodides of alkaline earth metals are fairly ionic. Their ionic character increases with increase in the size of cation. As we go down the group, the beryllium halides, on the other hand, are covalent because of the small size of their charge of Be2 positive ion. Being covalent, beryllium halides have lower melting and boiling point than other alkaline earth metals. Chlorides, the beryllium halides are only sparingly soluble in water, but they are freely soluble in ether and other organic solvents. Beryllium chloride has interesting structure in solid state and vapor state. In solid state, it has polymeric chain structure as shown in Fig 1. The chain arises because of free electrons pair on chlorine atom which form intermolecular coordinative covalent bond. In this case, each beryllium atom is considered to be sp3 hybridized and is tetrahedrally surrounded by four Cl atoms. The adjacent tetrahedral planes are at 90 degree to each other, and Cl-BeCl bond angle is 98 degree instead of normal 109.28 angle of a regular tetrahedron. The smaller angle gives stability to the structure because it lessens the repulsive interaction between neighboring Be atom in the chain by keeping them further apart. In the vapor phase, BeCl2 tends to form chloro-bridged dimer which dissociates into liner monomer at high temperature of the order of 925 degrees Celsius. In the vapor state, the liner BeCl2 molecule involves sp hybridization of beryllium. Most of the anhydrous halides of alkaline earth metal have fluoride type structure. Beryllium chloride chain structure may be broken by weak ligands such as Et2O, CH3 twice CO, CH3NO2 to form four coordinated molecular complexes as BeCl2L2, where L is the ligand, as well as by strong ligands like H2O, NH3, PY, etc. to form ionic complexes as BeL4 to positive Cl2 negative. In these complexes, beryllium is sp3 hybridized with tetrahedral arrangements of ligands. Anomalous behavior of beryllium and magnesium in diagonal relationships. Beryllium, the first member of the alkaline earth metals family, show anomalous behavior as compared to magnesium and the rest of the members. However, beryllium shows diagonal relationships with aluminium. It is mainly because of the following reasons. First, small size of the atom or its ion. Second, high ionization energy and electronegativity. Third, absence of d orbital. Some of the important differences between beryllium and magnesium are given below. First, beryllium is harder than magnesium. Second, it possesses higher boiling and melting point as compared to magnesium. Third, beryllium does not react with water even at elevated temperatures. On the other hand, magnesium react with boiling water. Mg plus 2H2O gives MgOH twice plus H2. Fourth, beryllium does not combine directly to form hydride whereas magnesium does. Fifth, beryllium forms covalent compounds while magnesium forms ionic compounds. Sixth, beryllium carbide with water gives methane while magnesium carbide gives acetylene. Be2C plus 2H2O gives 2BeO plus CH for methane. MgC2 plus 2H2O gives MgOH twice plus C2H2 acetylene. Seventh, BeO is amphoteric in nature while MgO is basic. Diagonal similarities of beryllium and aluminium. Beryllium shows some similarities with aluminium due to diagonal relationships. Some common examples are: first, both beryllium and aluminium form covalent compounds. Beryllium, like aluminium, is rendered passive on treatment with concentrated and HNO3. Both form complexes BeO and Al2O3 are amphoteric, that is, they dissolve in acid as well as in base. Fifth, the carbide of both B and aluminium liberated methane with water. Next, both the metals are weakly electropositive in nature. Seventh is beryllium and aluminium form fluorocomplex anions BeF4 2 negative and AlF6 3 negative in solution. The other group 2 metals do not form stable fluorocomplexes in solution. 8. Beryllium dissolves in alkalis to give berylate ion BeOH4 whole negative 2 negative, while aluminium dissolves to give AlOH6 whole thrice 3 negative. Ninth, BeCl2 like Al2Cl6 has a bridged polymeric structure. 10th, halides of both beryllium and aluminium have similar solubilities. Special features of hydrides of S block elements. All alkali metal combine with dry hydrogen to form hydrides of the general formula MH. 2M plus H2 gives 2MH. 2Li plus H2 gives, on heating at 873 Kelvin, gives 2LiH, and 2Na plus H2 on heating at 673 Kelvin gives 2NaH. The hydrides of alkaline earth metal are also prepared by heating metal with hydrogen. Mg plus H2 gives MgH2. Beryllium hydride is prepared as BeCl2 plus 2LiH gives BeH2 plus 2LiCl. BeCl2 plus LiAlH4 gives 2BeH2 plus LiCl plus AlCl3. Other elements of group 2 directly combine with hydrogen to form ionic hydride. CaH plus H2 on heating at 1073 Kelvin gives CaH2. Ba plus H2 on heating 1123 Kelvin gives BaH2. Calcium hydride CH2 is commonly known as hydrolith. Alkali metal hydrides are crystalline solids because they have ionic structure M positive H negative. The ionic character of the hydrides increases as we go down the group. The hydrides are not very stable. They react with water readily, liberating hydrogen. LiH plus H2O gives LiOH plus H2. Lithium also forms complex hydrides LiAl4, lithium aluminium hydride, which is used as a reducing agent. It is obtained from lithium hydride in dry ether as 4LiH plus AlCl3 at dry ether. In dry ether gives LiAlH4 plus 3LiCl. It is ionic and the AlH4 whole negative is tetrahedral. It is powerful reducing agent. LiAlH4 reduces carbonyl compounds to alcohols and reacts violently with water. It also reduces a number of inorganic compounds. BCl3 plus LiAlH4 gives P2H6 diborane. PCl3 plus LiAlH4 gives PH3 phosphine. Sodium also forms complex hydride NaBH4 sodium borohydride. It is the best prepared by the heating sodium hydride with trimethyl borate 4NaH plus BOCH3 whole thrice on heating between 250 to 270 degrees Celsius gives NaBH4 plus 3NaOCH3. It is also used as a reducing agent. Therefore, these hydrides are used as reducing agents in general. The reactivity of these hydrides increases down the group and therefore their reducing character also follows the same trend. In case of alkaline earth metal hydride, BeH2 is a covalent while MgH2 is a partially ionic. The hydride of calcium, strontium, and barium are largely ionic due to the greater electropositive character of the metals. The alkaline earth metal hydrides are reducing agents and are hydrolyzed by water liberating hydrogen. Therefore, they also react as reducing agent. BeH2 and MgH2 are examples of polymeric solids. BeH2 whole and polymeric has a very interesting structure as shown in Fig 4. Beryllium is bonded to four hydrogen atoms and hydrogen is forming two bonds. And the bond between two beryllium atoms and one hydrogen atom is a special type of bond known as three center electron pair bond, also called banana bond. It covers three atoms and quanta. CH2, BH2, and SRH2 are ionic solids, M2 positive and H negative. These have slightly distorted HCP and arrangement, solvation, and complexation tendencies. All the simple salt dissolved in water producing ions and therefore the solution conduct electricity. Now Li positive ion is small. It might be expected that the solution of lithium salts would conduct electricity more than the solutions of the same concentration salts of Na positive, K positive, Rb positive, and Cs positive ions. So salts. This is because the small ion should migrate more easily than larger ions and therefore conduct more than larger ions. However, the ionic mobility measurements in aqueous solution shows the result of opposite order as Cs positive is greater than Rb positive greater than K positive plus greater than Na positive greater than lithium positive. The main reason for this anomaly is that the ion in solution do not exist as bare ions but are hydrated or solvated. The solvation must be considered of two types. First, some solvent molecules are attracted by the metal ion and get bound to it, forming a complex. This is called primary solvation shell, and the solvent molecules get directly coordinated to the metal ion. For example, lithium ion, the primary solvation cell consists of four tetrahedrally arranged water molecules around Li positive ion. This is called hydrated ion and behaves as one entity. The Na positive and K positive ions also and may also have four coordinated primary shell. On the other hand, Rb positive and Cs positive ions form six coordinated shell having six more water molecules in the primary shell. The solvent molecules are bounded to metal and by electrostatic force of attraction. Second, beyond the primary solvation cell, the additional layers of the solvent molecules are bound to the primary shell, which further solvate the ions. This is called secondary solvation shell. The extent of secondary solvation appears to vary inversely with the size of the bare ion. Thus, with the increase in the radii of the ion, the total hydration numbers, hydrated radii, and hydration energy decreases. Thus, the extent of hydration decreases from lithium positive to cesium positive, and therefore the hydrated radii and hydration energies decreases from lithium to cesium positive. As hydrated radii decreases, ionic mobility increases. These trends are given in table 5. Thus, lithium positive is maximum hydrated and most slowest, while Cs positive ion is least hydrated and most moves fastest. Therefore, the ionic mobility decreases as Cs positive greater than Rb positive greater than K positive greater than Ni positive, Na positive greater than Li positive. Similarly, alkaline earth metal ion begin smaller than the alkali metal ions are hydrated to greater extent. It is not only because of their smaller size but also due to their change increased charge. As a result, the hydration energies of alkaline earth metal ions are about 4 to 5 times greater than those of the alkali metal ion. However, the hydration energy decreases down the group as the size of the ion increases. This is given below in table 6. The size of the solvated ions plays an important role in the behavior of alkali metal ion in ion exchange material and passes of the ion through cell walls and other biological membranes. For example, in cation exchange columns, larger Li positive hydrated ions are less strongly attached to the column and hence are elucidated first. Complexion of alkali metals ion bicyclic polyethers. In the mid 1960s, an important class of macrocyclic polyethers was developed by C.J. Pedersen. These were shown to form stable complexes with alkali metal cations. A typical example is a cyclic ether. This is also called as crown ether because of the crown shaped arrangement of metal complex. The stability of the complexes was found to depend upon the number and geometrical deposition of ether oxygen atoms, and in particular on the size and shape of the coordination polyhedra relative to the size of the cation. In Fig 5, crown ether diclohexyl 18 crown 6 is shown. In this case, numerical prefix indicates the number of atoms in the heterocyclic cycle, and the suffix numerical indicates the number of oxygen atoms. For example, in this case, it is 18 membered ring with the 6 oxygen atoms. Some other common crown ethers are also shown below without C and H atoms. The alkali metal ion binds to these polyethers by filling the center cavity of cyclic polyether and trying to interact with as many oxygen atoms as possible. The strongest binding occurs when the metal ion fits nicely into the cavity. The bonding between metal ion and cyclic polyether is largely electrostatic. For a cation to be tightly bound in the cyclic polyether, the size of the cation and the size of heterocyclic ring cavity size is important. Cryptates. There is another group of similar type of coordinating ligands which have been used to coordinate alkali metal ions. These are polycyclic ligands which contain, in addition to oxygen, other donor atoms such as N, P, or S. These are called cryptates. Thus, are polycyclic ligands which contain, in addition to oxygen, other donor atoms like N, P, or S. The name cryptate comes from the Greek word for hidden. In these structures, the metal ion is hidden in the structure. The cryptate are even more selective and stronger complexing agents than crown ether. The structure of one cryptate, 222 crypt, is shown in Fig 6. Sodium forms the compound Na222 crypt, positive Na negative in ethylamine solution. This is golden yellow diamagnetic solid which is stable up to minus 10 degrees Celsius. 2Na plus and C2H4O2 C2H4 whole thrice and gives it Na crypt positive Na negative. The interesting feature is that it contains sodide ion Na negative. Crystallographic studies have shown that the radius of Na negative ion is 2.3. In this, electron transfer occurs between two sodium atoms in the formation of sodide ion Na negative, as 2Na gives Na positive and Na negative. The large cryptate ligand completely shields the Na positive ion and prevents it from recombining with Na negative. Similarly, other alkali compounds containing K negative potasside, Rb negative rubidide, and Cs negative ceside have been paired. Unique characteristics of crown ether and cryptates. The crown ether and cryptates provide unusual solubilities in organic solvent. For example, sodium and potassium dissolve in ether to form only dilute solutions for 10 raised to power minus 4 m concentration. However, when a crown ether or cryptate is added, the concentration of alkali metal is dramatically increased by a factor of 10 raised to power 3 to 10 raised to power 4. The crown ether and cryptate have remarkable tendency to stabilize the large anions. The stabilities of these anions is attributed to the shielding effect of the cryptate on the cation. For example, the reaction 2Na gives Na positive plus Na negative in endothermic. However, in the presence of cryptate ligand, the compound Na the compound is obtained which is stable. In this complex, the large ligand completely isolates the cation so that the transfer of electron from Na negative to Na positive is prevented. Mixed cation anion systems may be also be prepared, such as K crypt positive and a negative. Differences between crypts and crown ethers. The cryptate ligands are better complexing agents than crown ethers because of the following reasons. First, cryptates have nitrogen as well as oxygen donor atoms and therefore are more selective and better complexing agents for alkali metal ions. Second, they are polycyclic and can surround the metal ion more firmly. Metals. In addition to binding of alkali metals to polycyclic ethers, these have very little coordinating ability because of their large size and low charge. Because of their low charge density, they are poor electron pair receptors and do not form complexes. However, it has been observed that they form complexes with chelating groups. These ligands are very strong complexing agents because they are multidentate and form a ring or a chelate compound by bonding to the metal ion. The metal generally attains a coordination number of 4 or 6. The common chelating ligands forming complexes with alkali metals ion are salicylate aldehyde, acetyl acetone, benzoyl acetone, methyl salate, or nitrophenol, or nitrosyrosol, etc. For example, when sodium hydroxide is added to salicylate, a sodium salt of salicylate is formed, which takes up a further molecule of salicylate to form a salicylate complex of sodium NaOC6H4CHO, HOC6H4H4CHO. Similarly, when anhydrous sodium derivatives of acetyl acetonate is hydrated, a dihydrated having 4 covalent bonds to sodium is formed. This is a covalent compound and is soluble in only non-polar solvents. Potassium, rubidium, and cesium also form 4 and 6 coordinated compounds with salicylate, a 6 coordinated compound of cesium. Trace cesium is shown in Fig 7. Complexion tendency of alkaline earth metals. Group 2 elements are not well known for their tendency to form complexes. Is Be is appreciably smaller than the other members and forms some complexes. Bef2 readily coordinates to two extra F negative ions forming the tetrahedral complexes Bef4 whole 2 negative ion. Bef2 plus 2F negative gives the Bef4 whole 2 negative ion compound. The complexes of the type BeCl2.De, where D is an ether aldehyde or ketone having donor O atom, are known. These complexes like BeH2O whole 4 uh, whole 2 positive are tetrahedral. Beryllium also form many stable chelate complexes with oxalate beta diatoms such as acetyl acetonate and with ketol. ketocol. In all these Be2 positive ion is tetrahedrally coordinated as shown in Fig 8. A complex with unusual structure is formed if BeOH2 is evaporated with acetic acid. It is known as basic beryllium acetate. Its structure comprises a central oxygen atom surrounded by 4 Be atoms located at the corners of a tetrahedron and 6 acetate groups arranged along the 6 edges of the tetrahedron. In Fig 10, Be4OCH3 COO whole 6 melts at 285 degrees Celsius and boils at 330 degrees Celsius. It is stable to heat and oxidation except under drastic conditions. It is slowly hydrolyzed by hot water but is decomposed rapidly by mineral acids to give an aqueous solution of the corresponding beryllium salt and free carboxylic acid. Basic beryllium nitrate has structure similar to that of basic beryllium acetate with bridging nitrate groups. It can be prepared by first dissolving BeCl2 in N2O4 ethyl acetate to give crystalline solvate, which on heating to 50 degrees Celsius gives BeNO3 which decomposes suddenly at 125 degrees Celsius into N2O4 and Be4O NO3 6. The sequence of reaction is shown below. BeCl2 and at N2O4 ethyl acetate gives BeNO3 whole twice dot 2 N2O4. After heating it gives BeNO3 whole twice, and the in after the heating under 125 degrees Celsius it gives Be4ONO3 whole 6 basic beryllium nitrate. Magnesium forms tetrahedral halide complexes such as C2H5 whole 4 and whole 2 MgCl4. However, the most important complex of magnesium is naturally occurring chlorophyll, the green pigment present in plants. Chlorophyll absorbs light in the red region from sunlight and makes the energy available for photosynthesis. In this process, CO2 is converted into sugars. CCO2, 6CO2 plus 6H2O. In the presence of chlorophyll and sunlight, it be- gives glucose C6H12O6 plus 6O2. Almost all life depends ultimately on chlorophyll and photosynthesis. In chlorophyll, magnesium is the center of a flat heterocyclic organic ring system called porphyrin, in which four nitrogens are bonded to the magnesium. Magnesium also forms complex with hexadentate EDTA having 6 donor atoms. EDTA also forms complexes with Ca2 positive, Sr2 positive and Ba2 positive ions. The water soluble complexes of EDTA are very important because of their analytical applications in determining hardness of water. Next is role of alkali and alkaline earth metal ion in biological system. Role of Na positive and Ka positive ions. Na positive and K positive ions play a very important role in living organisms, including human beings. 2. Sodium and potassium are quite similar in their chemical properties, yet their biological functions are very different. Na positive ion is a major cation of extracellular fluids of living organisms which activate certain enzymes in the body. The Na positive ions are actively expelled from the cell, whereas K positive are not. This ion transport is called sodium pump, and it involves both the active expulsion of Na positive ion and take up of K positive ion. As a result of this, it expels Na positive ion from intracellular fluids to the extracellular fluids with the help of carrier protein. At the same time, it takes up K positive ion into the intracellular fluids. Analysis of the fluids inside and outside animal cells shows that this type of ion transport really occurs. In animal cells, the concentration of K positive is about 0.15 mole and that of Na positive is about 0.01 mole. In the body fluids, outside the cell, the concentration of K positive and Na positive ions are about 0.004 mole and 0.15 mole respectively. The energy required for the transport is obtained by the hydrolysis of ATP. At it has been estimated that hydrolysis of one ATP molecule to ADP provides energy sufficient to expel 3 Na positive ions out of the cell and 2 K positive ions back into the cell. Since each operation of the pump expels large number of Na positive ions from the cell than the number of K positive ions that it pump into the cell acquires an excessive negative charge and the exterior of the cell acquires an excess positive charge. This results in the development of electrical potential across cell membrane, which is responsible for the functioning of nerve cells, nerve cells and muscle cells. K positive ions inside the cells are essential for the metabolism of glucose, synthesis of protein, and activation of some enzymes. Role of Mg2 positive and Ca2 positive ions. As already studied, magnesium is the most is an important constituent of chlorophyll, which is responsible for photosynthesis in green plants. Mg2 positive ions are concentrated more in the intracellular than in the extracellular fluids in animals' body. On the other hand, Ca2 positive ions are concentrated more in the body fluids outside the cell, similar to K positive ion and Na positive ions. The Mg2 positive ions help in the activation of phosphate transfer enzymes, which participate in the energy rel- releasing biochemical process occurring in animal bodies. Magnesium ion are also required for carbohydrate metabolism. Mg2 positive and Ca2 positive ions are responsible for the transmission of electrical impulses along the nerve fibers and for the concentration of muscles. Calcium ions are essential for the formation of bones and teeth as apatite Ca3PO4 whole 2 and the enamel on teeth as fluoroapatite Ca3PO4 whole twice dot CAF2 dot Ca2 positive ions. Ca2 positive ions are important in blood clotting and for maintaining the regular beating of the heart. Certain types of muscle cramps can be prevented by increasing the intake of Ca2 positive ions. Thank you.